In this video, I'm going to go over some tips for translating words or descriptions of equations / expressions into the actual equations and expressions. In order to do that, we need to be focused on keywords that mean certain things. So the first ones I'm going to talk about are addition. The keyword sum of means that we're going to add two things together. In this case, a number, which for all of these examples, we will just use the letter X to represent some number, and the number 7. So that translates to X plus 7. A number increased by also means addition. A number is going to be X, and we increase it by 2. 6 more than a number, another indication of addition, more than. X plus 6. A number plus 3. X plus 3. Let's move on to subtraction. Subtraction can be a little bit more confusing. And there's an important thing that we need to learn about the word than. 5 less than a number. Than is often referred to as a switch word. Means that the two values that were given, a number and 5, should be switched. So 5 less than a number turns into X minus 5. Notice how 5 was at the beginning of the statement and it ended up being subtracted. The difference of 8 and a number. We're going to take these in order. That's going to be 8 minus the number X. 8 minus X. A number less 3, X minus 3. The difference of a number and 2. Notice that this is very similar to the second statement up here, but in this case, a number comes before the value of 2. So in this case, the X is going to come first. We're going to take these in order. The difference of X and 2. X minus 2. Moving on to multiplication. 4 times a number. That's pretty easy. 4x. Twice a number or double a number would be the same thing. 2 times x. Twice or double just means multiply by 2. The product of 7 and a number. That's just 7x. That just means multiplication. 3/4 of a number. Now, of is another code word that you can look for that often means multiplication. So in this case, 3/4 times a number. 3/4 x. Half a number. Half means to multiply by 1/2. 1/2 x. Moving on to division. The quotient of a number and 4. Quotient is a strange word, but it just means that we're going to take the number and we're going to divide it by 4. The first thing goes on the top of a fraction. The second thing goes on the bottom. So that becomes x divided by 4 or x over 4. Half a number. Now, we already reviewed half of a number in multiplication, but we can also think of this as division. X divided by 2. 1/2 x and x divided by 2 are exactly the same thing. 1/3 of a number, x divided by 3. All right, there's a few more combinations I want to talk about before we get to example problems. 4 times a number is 16. In this case, I have the word is highlighted because it stands for the equal sign. So everything to the left of the word is going to be on the left side of the equation, and everything to the right of the word is going to be on the right side. So that turns into 4x equals 16. Finding the is and breaking it up into 2 parts can be very helpful. The sum of 2 times a number and 6 is equal to 4 times the number. Equal to also stands for the equal sign. So we're going to break this up into the left side and the right side. The left side says we're going to add 2 times a number and 6. The right side says 4 times a number. So that becomes 2x plus 6. We're summing 2 times the number and 6, and we're setting it equal to 4 times the number. In this video, I'm going to cover solving one-step equations. One-step equations just means that one math operation needs to be performed to both sides of the equation in order to find the value for the variable. So let's look at the steps for solving one-step equations. The first is to find what is being done to the variable. Now that variable may be x or y or a. It doesn't really matter, but we need to find the variable and decide what is being done with it. And then we're going to do the opposite of that math operation with the same number to both sides. If necessary, if we want to double check our work, we're going to substitute our answer back into the original equation and see if it makes it true. I will give you an example of that when we go through the problems on the next page. But here's some example equations that are one-step equations, and let's look at what is being done to the variable in each case. So in this example, y plus 3 equals 10, we are adding 3 to y. So we would want to do this opposite of that to both sides. The opposite of addition is subtraction, and we would subtract 3 from both sides. So we would subtract 3 here, and we would subtract 3 there. I'm not going to solve this because we'll do that on the next page. Let's look at this next one to the right. What's being done to the variable? We are subtracting 6. That means we should do the opposite, which is addition, and the same number. We should add 6 to both sides. Next one, x is being divided by 6. The opposite of division is multiplication, so we should multiply both sides by 6. Like that. And finally, in this last example, a is the variable. It's being multiplied by 5. So we should divide both sides by 5 because division is the opposite of multiplication. Now, let me show you why we're doing this. We're doing it because it's going to cancel everything but the variable on the side with the variable. These two things will cancel each other out in every case here. And then we're just left with our variable equals some math operation on the other side. So we just need to simplify that other side, and that will tell us what the variable value must be. In this video, we're going to review the method of solving two-step equations. So the steps of solving two-step equations are: first, find out what was done to the variable side last. That's a little bit confusing right now. Through the examples, hopefully that will make sense. We're going to do the opposite of that to both sides. That will be our first step. And after that, when you simplify, you should have a one-step equation. Only one math operation will need to be done in order to solve for the variable. So let's go through an example here of that, what is being done to the variable side last. Using order of operations, if we were to solve for this expression over here, let's say if we know that y is equal to 3, we would have 2 times 3 plus 6. And in order to perform this math, we would multiply the 2 and the 3 first, and we would add the 6 last. That's why we refer to the addition of 6 in this case to be the thing that was done last. So that's the thing that we want to perform the opposite operation on first. We want to get rid of that plus 6. So by subtracting 6 from both sides, that will cancel this one out. and we will be left with 2y is equal to positive 6. Now, this looks like a one-step equation, and it is. We have y being multiplied by 2. We can cancel that out by dividing it by 2, but we also have to divide the other side by 2. And we're left with y is equal to 6 divided by 2, or y is equal to 3. First step was to subtract 6 from both sides. Second step was to divide both sides by 2. 3x plus 5 is equal to 17. And we could see that, much like in the previous example, 5 is being added to the side with the x. We can simplify this by subtracting 5 from both sides. Cancels this out, and we would be left with 3x is equal to 17 minus 5, which is 12. Now we have a familiar one-step equation. Change my color here to show that next operation. We want to divide both sides by 3 because x is being multiplied by 3. And we know if we do that, that will cancel that out and leave us with x all by itself, which is the goal of this process, to get x all by itself. And x is equal to 4 would be our answer. Let's take a look at the next problem. X divided by 4 plus 3 is equal to 2. Once again, we are going to subtract from both sides. In this case, we're going to subtract 3 to cancel that addition of 3 out. And we have x divided by 4 is equal to negative 1. 2 minus 3 is negative 1. Now, this is different. We haven't seen this too often. X is being divided by 4. In order to cancel that out, we're going to have to multiply by 4. The opposite of division is multiplication. So let's multiply both sides by 4. Cancels that out, and we get x is equal to negative 4. This video is a short introduction to the concept of inequalities. We're going to start talking about inequalities with phrases, and then we're going to translate phrases like less than 2 to a math statement. So we would say a number is less than 2 translates to x. This is the less than symbol, and then the number 2. So we're also going to talk about how that looks on a number line. So there's a number line. And we put a circle without any filling in the circle, what we would call a hollow circle, at the number 2, because we're talking about the number 2. And then we draw an arrow to the left to indicate that any number less than the number 2 is part of the solution to this inequality. So notice that the direction of the arrow is consistent with the direction of the symbol. This symbol is also pointing to the left. So the two key things here is that the circle's not filled in because there's no line underneath this less than symbol, which would indicate less than or equal. And the arrow is pointing to the left and the symbol is pointing to the left. So let's go through and look at some other variations of inequalities involving the number 2. The second one is less than or equal to 2. What does that look like? That's what the math statement looks like, less than. Notice that our less than symbol now has the line underneath it. That line means or equal. Kind of makes sense because that's part of an equal sign, that straight line. There's our number line. We use a filled in circle now with that underlined symbol, and we're still going to the left. Notice it's still consistent with the direction of this symbol. I think that's the easiest way to remember which way the arrow goes. Next one is just equals to 2. We're familiar with that one. X is equal to 2. There's our number line. It's just a filled in circle at the number 2. There is no arrow. That is the solution. X is equal to 2. Next one, greater than or equal to 2. That's what that looks like as a math statement. X, this is the greater than or equal symbol, and the number 2. Notice we have an underline. There's our number line. We filled in the circle at the number 2 because 2 is included. And our arrow now goes to the right. Notice that that is consistent with the direction of this symbol. That's also pointing to the right. Last one, greater than 2. That's the math statement. X greater than, no underline, the number 2. There's our number line, a hollow circle indicating that 2 is not included, but an arrow going to the right indicating that all numbers to the right of 2 or larger than 2 are included in the solution. All right, hopefully that was a good overview of those symbols. Let's go through just a few examples here. Which number line matches the expression X? This symbol means less than -1. So we know we're talking about -1, and we'll notice that all of our circles here are at -1. So that doesn't eliminate anything. Our symbol is pointed to the left. That eliminates C and D because those symbols are pointing, or those arrows are pointing to the right. So we can eliminate C and D. Notice that A and B are pointing to the left. The other thing we want to look at is it or equal? And it is not, because we do not have that line at the bottom of the symbol. That means we're going to have a hollow circle, a non-filled in circle. That eliminates answer A, and B is the correct answer to that question. This is the second video on inequalities. In this video, we are going to talk about translating inequality statements from word problems and solving those inequalities. So an important aspect of translating is that we have to connect keyword phrases with the operator, the inequality operator. What do I mean by the operator? That's these guys, greater than, less than, greater than or equal to, and less than or equal to. So we want to look for words like more than in the word problem that are going to connect us back to that operator. For less than, we might be looking for a word like below or fewer than that would give us a clue that we are talking about that operator. Common phrases for greater than or equal to, at least, or minimum. And for less than or equal to, at most, and maximum. Now, I'm not going over all of these. If this is new to you and you haven't seen this before, or if it feels like you need a refresher on it, I would encourage you to stop the video or pause the video, take a screenshot of this, take some time to study these phrases so that you're more familiar with which one connects with which operator. So let's just make a simple example here. This statement over here, wash your hands for at least 30 seconds. Which of these operators would we use? Well, we can see that at least is in this group. That means it should be greater than or equal to. And we are greater than or equal to the number 30. Now, often when we build these statements, we will include a variable in it, like x. X is greater than or equal to 30. Now, if you're having some trouble picking from these, try to keep in mind what values would be true for this statement. If you want, which values would be okay? If you washed your hands for 30 seconds, is that okay? Yes, it says at least 30 seconds. 30 seconds is good. 31 is also good, or 32, or 60, or 5 minutes would be good. Any number larger than 30 seconds is good. It makes this statement true. All right, with that, let's move on to a more typical example of a word problem. A kid's party place charges $40 for the room, plus $6 per child who attends a party. Joe wants to spend no more than $110 on a birthday party. What inequality expression could be used to find the number of children, and we're going to let the number of children be the variable C, who could attend with that budget? All right, in a problem like this, we should focus on putting the cost statement on the left-hand side. And what I'm going to do is to say, well, if it's $6 per child, we want to multiply 6 times C. That's going to tell us the cost that's based on the number of children. But then there's an additional cost, right? They're charging $40 just for the room. So we better add that. So the total cost for this party is going to be $6 times the number of children, C, plus $40. Now, Joe wants to spend no more than $110. Notice that no more than is right here. No more than connects with the less than or equal to. So Joe's okay spending $110, but she's also okay spending less than $110. So it makes perfect sense, less than or equal to $110. And that's how we build an inequality statement out of a word problem. In this video, we are going to talk about working with math functions, in particular, working with function notation. First of all, what is a function? You can consider a function to be like a math machine that produces an answer based on some inputs. So here's an example of a function. Don't focus too much on this notation. That's the function notation that we will cover in a moment. But here's the heart of our function, 200h plus 50p. In order to use this function or machine, we need to know what h and p are. So we call those inputs. H is equal to 3, p is equal to 30. Once we know that, we can substitute and do the math. 200 times 3 plus 50 times 30 is going to give us our answer. We evaluate that in the calculator, and we get our answer of 2,100. That's all there is to it. So let's take a look now at that function notation. Here's an example. F of x equals 4x minus 10. Now, the right-hand side of this equation probably looks pretty familiar to you, but this left-hand side, which is the function notation, looks kind of weird. What does this f of x mean? Well, it's really the same as the y that you've seen before. Y equals 4x minus 10 probably looks very familiar to you, but we've basically replaced y with this f of x. So let's explain why somebody might do that. It's just another way to write an equation. There really isn't much of a difference between these two. F of x just means there is a function and its name is f, and it depends on the value of x. That's all it means. Functions can use different function letters and variables. For example, we could say g of a, the function g depends on the variable a. C of x comma y. The function c depends on the variables x and y. A function can have more than one variable. Here's another one. A, and here we have a capital A. It doesn't matter whether we use a lowercase or a capital letter for our function. The function A depends on the variable